So another way to look at the delta H, or the change in enthalpy for a reaction, is to use what are called the standard heats of formation. So a standard heat of formation is the change in enthalpy, or the change in energy, during the formation of 1 mole of a compound at 25 degrees Celsius. So it's a constant. It's specific for a particular substance, and it's when you're trying to form 1 mole of that substance at 25 degrees Celsius. That's the amount of energy that it requires. And it's symbolized by delta HF, so change in heat of formation, and then the knot, the circle at the top, that means standard. So it's a standard heat of formation. When we go to find the overall reaction, it's always the heat of formation of the products minus the heat of formation of the reactants. So you're going to add up the total heat of formation for all of your products, and then you're going to add up your total heat of formation for all of your reactants, and then you're going to subtract the two. So that gets you delta H naught, or delta H standard, for that particular reaction. So let's walk through a couple of examples. So the first example says, what is the standard heat of reaction, or heat of formation, for 2 carbon monoxide reacting with oxygen gas to form 2 carbon dioxides? When we do this, we're going to refer to a table of standard heats of formation. So in your homework, you'll have a picture of a table that has all of the heats of formation that you need. For these particular examples, I went ahead and just wrote the list out on the side. So remember, our formula is the overall heat of reaction is the heats of formation for the products minus the heats of formation for the reactants. So let's plug our numbers in. Now, for my products, I only have 1 product, so I'm looking at carbon dioxide, and I produce 2 of them. So I'm going to take 2, because I have 2 carbon dioxides that I produce, or 2 moles of carbon dioxide that I produce.
L'Aquarius Bradford, please report to the lower main office. L'Aquarius Bradford, please report to the lower main office.
Apologies. We'll keep going. So you produce 2 carbon dioxides, or 2 moles of carbon dioxide, and for every 1, it releases 393.5 kilojoules of energy. So I'm going to do 2 times negative 393.5. So those are my products, and then I have 2 reactants. So I'm going to do the same thing. 2 times the heat of formation for carbon monoxide, which is negative 110.5 kilojoules. And then I'm going to add in my oxygen. Oxygen is 0. Any element, including the diatomics, so any diatomic gas or any element that's just on its own, has a heat of formation of 0. So that makes that easy. So now all I have to do is do the math. So 2 times negative 393.5 gets me negative 787.0 kilojoules. And then 2 times negative 110.5 gets me negative 221.0 kilojoules of energy. Notice it's a minus a negative number, so make sure you type that into your calculator correctly. And overall, this becomes negative 566.0 kilojoules of energy. So all I had to do was plug in the numbers for my products and my reactants, make sure I multiplied by the coefficient, and then crunch the numbers, do the math. Let's look at another example. So this example says calculate the standard heat of reaction for calcium carbonate solid decomposing into solid calcium oxide and carbon dioxide gas. So here are your standard heats of formation. And remember, here's your equation. I want you to try this one on your own, and then we're going to check your answer in a second. So let's walk through this one. So my delta H is always my products minus my reactants. Now I have 2 products in this case, so we're going to take it one at a time. I'm going to do my calcium oxide first. I have 1 calcium oxide, so I'm going to multiply 1 times negative 393.5 kilojoules, because that's my value for calcium oxide. And then I'm going to add to that 1, because there's an imaginary 1 there, times the heat of formation for my carbon dioxide, so negative 635.1 kilojoules. And then from that total, I'm going to subtract. There's also a 1 in here, so 1, and then my calcium carbonate, so negative 1,207 kilojoules. If I add up this side of the reaction, I get negative 1,028.6 kilojoules of energy from my products. And then there's no math to do over here because it's just 1 times negative 1,207. So it just stays as negative 1,207 kilojoules. So negative 1,028.6 minus a negative 1,207 gets me an overall delta H of 178.4 kilojoules of energy. Let's look at our third example. So example 3 says calculate the standard heat of reaction for 2 nitrogen monoxides reacting with oxygen gas to form 2 nitrogen dioxides. So same thing, here are your values. Your equation is always products minus reactants. Let's see what we get. Okay, so my products, I only have one product, and it has a coefficient of 2 in front of it, so I'm going to do 2 times the value for NO2, which is 33.85 kilojoules. And then I'm going to subtract from that my reactants. So I have 2 reactants. My first one is nitrogen monoxide, and there are 2 of them. So I'm going to do 2 times the value of 90.37 kilojoules. And then I'm going to add to that my value for oxygen, and oxygen's just 0, so I'm adding to it 0. Now if I crunch the numbers, 2 times 33.85 gets me 67.7 kilojoules of energy, and then subtract off my reactants. 2 times 90.37 gets me 180.74 kilojoules of energy. 67.7 minus 180 gets me an overall delta H of negative 113 kilojoules of energy. So it's always products minus reactants, and these numbers here you're going to get from a table or they'll be given to you, and then you just have to remember to multiply each value by the coefficient that's in front of that particular substance in the reaction. So you want to make sure you have a balanced reaction, then you're going to use the coefficients and the constants, and it's always the sum of the products minus the sum of the reactants.